So I'd probably be done this day, but. I'm sorry.
There was one word that you used in like one, it was like one word, you had like answers and the question.
Oh, well, I didn't. Yeah.
What?
Did it have like
What?
a draft completed before? Or if it
When you did it?
the draft.
On the computer, it's 10. So, your computer did what?
It was like 2 words, but I saw it.
So now it doesn't try.
I'm not sure.
No, it's
They had that close here.
because you can. That's when catch read.
Sitting with me, like right in the podium. And I'm like watching him do this the whole time. Like his
That's why catch read. Dog would never do that.
dog was true.
A puppy, maybe. But a dog, we're talking dogs. Yeah, and you said that cats are evil and they will forever be evil.
It's been a long time.
Today after class, I will, because I legal research I'll just go, oh my god, I'm done, like, that's really like a review. And they'll just be like, maybe we should like, I have an hour to read this class and I'll go over what I read. That hour's just gonna be. And if it's not. What is that? Is that, do you know this one or not? No, it's not a picture. This weird photography.
You guys take photos?
No, we learned about photos.
Do you think you can talk a lot about this?
Probably.
And it's double spaced, right?
Yeah.
It's only like 15 minutes. Double spaced.
Double space. So 30 times 7, 21. Yeah, you know that. 1,000 words is easy.
I think so.
Agriculture.
If you finish your classes today, you can. Yes. Those are the open ones.
Very proud.
That's wise. I mean, it's not fair for taking.
All right. It is 8:06. Hopefully your peers get here, but let's get started. So as a reminder, I say this every single class, but don't forget to check what's upcoming. Like on Wednesday, you have your next video, and then next Monday, you have one more, and then that's it for the semester. And then this is a good time to start practicing for the final. I know it's not for another 2 weeks, but you're talking about an entire semester of material that you need to review and practice for the final. On Canvas are several extra credit opportunities, like I mentioned before Thanksgiving, so please check them out. We're supposed to have a seminar coming up. Once I get that information, I'll post it. And last class, we got through a chunk of chapter 10. We're gonna finish that up. But chapter 10 at the end relates directly to chapter 27, so you might see some of that material kind of overlapping with each other. Also, if you need to come and see me, whether it is to go over material or ask questions, or if you don't really know what your question is, but you need to go over stuff, to come and see me, or or you can go to S Cubed. All of the information about S Cubed is on the portal. All right, so we are going to get into more problems on chapter 10. Some of what we're going to do today is just mostly review problems. And then there may be some overlap into chapter 27, but a lot of that will be next class. So the molecule of the week last week, we had talked about how to initiate radical reactions, and the best way to initiate radical reactions is with peroxides. And peroxides, we can split with light or heat. If you're just talking about hydrogen peroxide, actually it doesn't really do this very much. It's not good at doing this. Hydrogen peroxide is actually just an oxidant usually, so it's not very good at doing redox reactions. It can to some extent, but not too much. So as we start adding different R groups, it actually improves this. But the one that we talked about, and this was our molecule of the week, dibenzoyl peroxide, which people actually use in pharmaceuticals as well, is easy to split in our initiation phase because we have a whole bunch of resonance, we have induction, we have all sorts of things going here that makes this bond fairly weak. So we talked about that as our molecule of the week last week, although we only had one class last week. Today's molecule of the week is kind of the opposite. So this is an initiator. Our molecule of the week, BHT, which is going to have terbutyls, methyl group, and it's a phenol. That phenol is actually what's doing the work. So this bond right here, we've seen this in chapter 3, that phenols are actually somewhat acidic, so this bond is fairly weak. So it's very easy to remove, if you have some sort of radical, to remove that hydrogen, to abstract that hydrogen and give the oxygen, make it a radical. And the reason that this is a good molecule for actually stopping radical reactions is because once you make that oxygen a radical, it's highly resonance stabilized, as well as this molecule being so bulky, it's hard to do anything anyway. So between resonance stabilization and the bulkiness of this molecule, it makes it very good for this molecule to be actually used to stop radical reactions. So you see people using them as antioxidants. We'll talk about some natural antioxidants in a little bit. But it is a compound as well as some other kind of compounds that are similar to this that people use in food preservatives. They put in medical related preservatives. But also we've seen people use these kinds of compounds for other reasons that are antioxidant reasons. And some of your diseases, for instance, are actually caused by redox reactions. And these kinds of compounds we often see as treatments for certain types, or we believe are treatments for certain types of diseases to either slow them, not necessarily to stop them. So we do see people using them for certain types of viruses like herpes, cold sores. We see people using them with AIDS, but not, again, not to stop it, but to kind of slow its behavior. So, for the same purpose of it being an antioxidant, it's hope that we do use it for that behavior. All right, so I'm gonna have you guys go back to opening that worksheet that we were working on before, and then there's some problems that I'm gonna do, there's some problems that you're gonna do. We left off on the page that says Anti-Markovnikov edition of HBR. So go back to that page, and then periodically we'll stop, we'll go over stuff. So the page that says Anti-Markovnikov edition of HBR, we're gonna continue on from there and just keep going. I think some of you already did this page. If not, just keep going. And then I'll stop you periodically. This is not a test, so talk to your peers. Should be a discussion. Should be trying to draw the propagation step. The
So I know there's a radical carbon, but then a bond is created, right? So is that still, that's the bond that's created with the other, electrons coming from the.
Yeah. So it's attaching to the hydrogen. Oh, you're breathing. And then that one has to go back into the carbon. Yeah. And then the carbon.
That radical is what attaches with protein.
It's technically two steps, but I agree with that. When we're doing these, we're drawing on from the bond itself, right? 'Cause that's what the electrons are doing.
Rather than from the.
Yeah, because that one is really have to work.
Should we run that propagation step? You should talk to your peers. You have no clue. You don't remember this from your video. You probably need to talk to your partner.
What do you mean?
So is the final steps being shown considered to be like?
We almost finished that page.
Oh, no, we have a Viera.
Very few people drawing any mechanisms. I don't know if the final step that we're being shown is determined needed, or if we need to turn the order on this. But I don't think we can do much from that. Maybe it's just understood. So it doesn't result in, where does the bromine run? Where would the bromine run? Like, if we were doing. Yeah. I get what you're saying, and it seems to make sense, but also,
Yeah.
like, I can't see where there's. If she comes around, I'll just ask her. If it's just so much further behind. Oh.
You and I should
Professor,
Hmm?
for number one, we're talking about the propagation steps. We did this. Is this final step the terminated? Okay, so then it's not. Right, so it's just that.
So you're supposed to be Well, I can see it just from the view, closer to do it. I don't know, it's just. I try to get my cancer or something.
This came straight from that. All right, a lot of you are not even close to even starting, and that's not good. So this mechanism I actually drew for you already in one of your videos. So we're gonna try to draw this together to get you going, because I think we're a little asleep today. All right, so what is a hint is actually on the bottom of the page. What is the initiation phase of this reaction? A hint is on the bottom of the page. That's not what the question is asking you. I'm asking you, what is the initiation? The bromine splitting apart, okay? That's your first step, okay? So, the question is asking you, what is the propagation phase? So we've just formed Br radical, and you have this, and there's a hydrogen coming off. There's some hydrogens coming off here. Oops. That's not what I meant to do. All right, so you have the bromine radical, and we're going to abstract some hydrogens. So our next step, was that we abstract one of the hydrogens. So we have two possibilities of places that we can abstract hydrogens from, and when we're done, so if we look at the first one, if you look at the first product, that double bond is still there. So we must have been removing this hydrogen, and that leads to this. The second one is adding the hydrogen on the anti-Markovnikov position. That means I must have done something to this double bond, okay? So the first one, this was reaction 1, that must have been the first step. For this one, I must have removed one of the 2 hydrogens. So I'm going to actually draw 2 possibilities. So I can remove that hydrogen and get this thing. I'm going to redraw this whole thing. So I'm only going to draw 1 hydrogen in here. And then over here, I'm going to take one of these hydrogens. So this is reaction 1, this is reaction 2, but I'm going to have 2 pathways. So for this one, I'm going to end up with I made a mistake right here. Let me fix this. Ignore this. Let me redraw this. I don't know why my eraser's not working. Anyway, ignore what's right here. So I can either get this radical like this, that's one propagation step, or if I remove this, get this double bond reacting like this and put the radical there, you get this one. So in pathway where I add the bromine, in this case, I forgot the bromine, I'm sorry. When I add the bromine in the less substituted, I get this secondary radical, and over here, if I add the bromine here, I get this primary radical. Which one is going to be more favorable? We can get primary and secondary radicals, but which one is more stable? Secondary. So this one is the best. So when you add your hydrogen, in that position right there, so when you add the hydrogen there, what kind of product is this across the double bond? Anti-Markovnikov, right? So that's what this question is eventually leading you to. So it is asking you for, in question number 2, explain why the following radical, which you see the radical in the primary position, why is this not produced in this reaction? Why is it not produced? What did we just say? It's less stable, right? So we said it's less stable. If it's less stable, is it going to be the preferred? Only like 20% of you actually answered that question. The less stable product, is it gonna always be preferred? No, right? So this is a little bit more stable. That's why you get the anti-Markovnikov product, okay? We always get the anti-Markovnikov product because of the stability of our molecule, all right? It's gonna be our major product for that reason. So our initiation is the bromine breaking apart. Then you can have two possibilities of reaction. You can have reaction 1, although the question is not really asking you, this third question is not asking about reaction 1, it's asking about reaction 2. And then when we go down to the bottom, it says basically that you have bromine being broken apart by homolysis, so we talked about that last time. And you see that the equilibrium arrow is going more towards the original bromine. So, because it's saying that, what does that tell you about bromine radicals being formed? Is that very easy to form? No, okay? So, that's going to be something that we're going to go back to and pick up on the next page. And it has to do with that molecule that I just talked about. It was our molecule of the week last week. So benzoyl peroxide, we talked about that. Notice something about the arrow. It's still going a little bit more backwards, but compared to our previous arrow, it's still forming a little bit more, okay? So I'm gonna give you a second to read through the part that says bond dissociation, if you haven't already read through that. And come up with an explanation. So you're gonna, with your groups, answer the next couple questions. Come up with an explanation for why we may choose benzoyl peroxide over bromine using that bond dissociation information. So I'm gonna give you a few minutes to answer question 4, and then try to do question number 5. Okay. So take about 5 minutes. Make sure you come up with an explanation and then try to draw your own mechanism for question number 5.
And then we break up the double bond. So it takes the hydrogen. Oh, it leaves the.
Because it's initiated, like the radical initiated. So, and otherwise that H would just dissociate. That's not what hydrogen does. Goes backwards, that one.
And the
Hmm?
is putting the ER.
No, this is the propagation site that we want. Yeah. No.
What's the determination?
All right, I drew a hint on the board for the second one. Second question. I'm gonna give you a couple more minutes to draw, and then we're gonna move to the next thing.
That's the target. Oh, because then that needs to do possibly. Where it takes the double bond. Because the peroxide is going to do that again with the HBr.
So this was the termination.
No, that's the propagation.
The termination is having the BR, like, basically get rid of the radical. Because there's gonna be a radical left with that tertiary. No, look at the ring. See where the double bond is? And then half, like, where the sugar ring is going towards that tertiary carbon, which means that the radical is going back to the one. So then the radical stays on it, so because the radical is left, it's only that propagation.
It's only propagation.
Yeah, because the radical isn't,
So I don't have termination?
I can just create something from nothing.
well, it's not telling us to draw the termination here.
But this.
I'm just curious what it would be.
Are you saying this?
Oh, it says two possible terminations.
Yeah, it says propagation step that leads to the product shown,
Propagation and like termination.
which would be this one, and then
this breaks apart.
two possible
Yes.
termination
So-
steps. So then you
So this
do termination after that.
What?
I'm not sure how to do that.
This is gonna do what you said.
So this is the first part.
Reaction. This is what we already did.
Right.
That's
Okay.
and the propagation stuff is
still be BR because it's not
So the place that we had it last time.
Oh, no, the H will go.
Yeah, it's all H goes to the.
RO. But then it becomes congregation stuff. That we want. Oh, that's what I'm doing.
Yeah. Disregard that last one, because obviously, like I said, already set up. Next one. That's true.
Did you look at this bird? Did you look at this bird? I kinda miss that.
Well, I'm not sure, because I used OR and you used the, oh, I guess R is, yeah.
I used the ROR here, which then split into the OR.
Yeah.
Which is then used with HBR to create
OR
ROH.
is to take the hydrogen. And then I did that.
And then that
What did you do?
So, to create, to get rid of the radical here and just make it into a BR bonus.
Literally, something just came from nothing. I caught it.
I guess if there's a lot of BR radicals in there, it's much more sense. Like a, this stuff. Because it's like, once the hydrogen is added, which gets rid of the radical.
No,
X is HBr. So you use one of these.
Like there's no
Which one of these are?
So the
Yeah,
X
so
is
you're
the
gonna
other
use
two.
the HOR.
Then it's gonna pick up the hydrogen thing.
Wait, but that's all.
That's
Just say X.
but then it's
So
always
it's
like,
like-
you have all sorts.
Yeah, if you look here, the reactions just be really powerful.
Basically,
Why don't we just
anything that.
attach it?
But to be fair, I think there were two.
There we go, number 3.
Wait, you can't, it's possible.
So there is
Why is it possible? Because you can't see
there are
this.
some
So
other,
you can't see
any of these that are left over attached to each other.
Because I don't have
Just anything.
you can't see any of this stuff when it's actually happening. So
There's a whole lot of different.
Probably.
I think,
they're
the
imaginary.
thing is that
They're scary. I don't like imagination.
because the termination step is when two radicals.
Got an
I was
imagination.
good for
Basically cancel each other out. And that's not what you have going on.
That's such a squirrel.
I mean, it
I don't know,
really.
I don't know what's right.
These OR and these BR. I never know both of those radicals in my system.
Yeah, because you see right here, we only use
There's
one of these
like-
dudes, so we're gonna use the other one. But you bring it. We only use
So it doesn't
one.
have.
So we gotta use the other one.
But it's multiple choice.
And that one's
So you have to know what it is.
Wait. No, that doesn't work. Do you know that?
All right, guys, what is the correct answer for number 4? Why is benzoyl peroxide chosen for these reactions? Because lower energy, so if it has a lower energy to break, why do we use it? It's easier to break, okay? So if we look at our mechanism, our first step is we take our initiator, we break it apart. That initiator is going to extract a hydrogen from here, make a bromine radical. We saw this previously, that bromine radical will attack the double bond and you'll get a secondary radical. And then we can use another HBr to protonate, right? But what are the termination steps? There are actually, it says 2, but there could be lots of different ones. What could be some termination steps?
2 bromine radicals.
2 bromines coming together, what else? There's no chlorine in there. Nice try. ORs can come together. What else? Pretty much any radical that sits in there can come together, right? Most of those are not going to be anything of significance that we're worried about, but they can form anything that's a radical. Coming together is a termination, right? Even if you only get 0.0001% of it happening, it is a termination, okay? our product actually comes after this step. You get a radical and then you protonate that radical, very similar to what we see over there, okay? All right, let's look at the things below. It says hydrogenation at the allylic and benzylic position. Last time we talked about NBS is the best way to put a bromine, or if you use NCS, a chlorine, NIS, iodine in the allylic and benzylic position. And it's going to be favored in that position because of the stability of the radical that we're going to form in the mechanism. And you'll read this on the next slide in a second. But the reason we use NBS, there is a little bit of stuff that is not 100% sure known about why this happens, but we do know that the structure breaks apart so little at a time that you get very little concentration of bromine radical, which kind of causes you to force the reaction to happen at the allylic and the benzylic position. So before we get into that, let's do a couple of questions that are review questions. I'm going to give you a moment to look at this, and then we're going to answer this question. And then I have another one after this. So look at this structure. So we're going to get a radical bromination. What must the product be? So think about it for a second. And if you remember something I said about this, you can figure the answer out very easily. All right, so when we add bromine onto our molecule, what part of the molecule is going to have a preference for that bromine in the end? Remember, bromine is extremely selective. It was like 2,000 times than any primary position. So which position? The tertiary position. So we're going to end up adding a bromine here. First, we make it a radical at that position, and then add the bromine. Which means when the bromine comes in, remember we talked about this last time, when the bromine comes in, which direction is it going to come in? Is it going to come in from the top? Is it going to come in from the bottom? No preference. So, in terms of stereochemistry, there's no preference. So what has to be the answer without even looking through the full name? The last one, right? Because there is no preference for stereochemistry. Very good. Yeah.
Also, there's no chiral center in this molecule, right?
Yes, there's also no chiral center. All right, here's another question. So review before we move on to our resonance structures. So you actually had this as a classwork question. There is a big difference between chlorine and bromine. Chlorine is not selective. It will pretty much go everywhere, okay? So if we look at our products in this case, we're gonna get multiple products. So if we look at this one, will we get this product? Yes, we will still get the tertiary. I said it's not selective, but you will still get it, right? Will we get this product where it's on that primary position? Yes, we will still get it. Will you, and I'm going to come back to this, these are the same. However, since I'm not adding anything at this position, this stereochemistry is not touched. So, will we get this dash? No, you can't. Unless I'm changing this chiral center, which I'm not, this wedge needs to stay there. So this is actually out of our running. Okay? This one, we're just adding the chlorine here. We're not touching that stereochemistry. We're just adding it on the end. So we will get that primary. What about this last one? Next one. Will we get that? So we're forming a radical here. And we can add on any side when we get that product. Yes, we will, right? Because we can get it either the chlorine coming towards you or behind you, so we will get this. Can we get that one where the chlorine's on the secondary position? Yes, we can. The only one we can't get is this one, okay? All right, so before we go to this question, we're gonna go through our radical resonance structures. So I'm gonna give you a second, look through these. So we've drawn resonance structures before. I'm gonna give you a second for the first one. You're gonna end up drawing 2 additional resonance structures, and for the next one, you're just gonna draw 1. So take a minute with your group and draw those resonance structures. What are the resonance structures for the allylic and the benzoic? There should be, the first one I have the arrows drawn for you, to D to the second, and then you're going to draw the next set of arrows to the third, and then to the fourth. The allylic only has 1 resonance, and that's important. Make sure everybody in your group can draw those resonance structures. Give you about a minute. Or 2. When you're done drawing the resonance structures, just read through the next page.
No, I'm saying, oh, you just, never mind, the second one you just went back to the original.
Yeah.
All right, but then, so like we said, there's 2 more resonance structures, to give you a total of 4 structures. The allylic has 1 more resonance structures, to give you a total of 2 structures. So which one is more stable, the allylic radical or the benzoic radical? The benzoic. There's more resonance structures that you can draw. I'm going to ask you to take a couple minutes to read the next page and draw that mechanism on the next page. And then we'll go over I'll do some problems for you. That's all the rest of the hand. this mechanism, it shows you first that the NBS breaks up in lighter heat. It's a very small amount that breaks up. This is what we believe is the reason why this reaction happens. But you end up with a bromine radical, and it tells you end up with this thing. How must that have happened? What must I be doing? How did you draw your arrows?
Bonding with hydrogen.
You're gonna end up bonding the bromine to hydrogen, but how is the arrows drawn?
So the arrow from the bond between the hydrogen and the carbon
Mm-hmm.
is going to be a fish hook to the middle, and then from the radical.
Very good. One more arrow.
Oh, and then it's going to go from that bond onto that carbon.
Very good. All right. So it says our second step, we take Br2, and we're going to get our product. What must be the mechanism arrow for that? Pay attention to the product.
You have to split up the buildings.
So you're going to end up splitting the bromine, but it's not happening. So this is all happening at one time. So yes, we're going to split the bromine, but something else is happening at this stage. Yes. This is going to come like that. You're going to form a bond with the bromine and then split the other bromine off. Okay? All right. So we're going to do a few problems, and some of these are actually, if you go through the rest of your worksheet, some of these problems are on the worksheet. So our first problem that we're going to do is we're given this tribenzyl methyl radical. This is actually one of the few radicals that we know exist for a long period of time just because of the resonance stabilization throughout all the benzenes. But we would probably predict once this happens that two of these structures will come together and give you that thing. But it turns out one of the products that we get out of this reaction is this thing, which does not look like that, right? We notice that you have this carbon and it's attached to a benzene ring. So something else must be happening here that is causing this process to happen. So if I were to figure out what's going to happen here, we're taking one of these, and remember I said that radical is highly resonance stabilized. If the aromatic ring is going to, benzene ring is going to be attached here, like we see this ring is attached to that carbon, there had to be a resonance on that ring, right? So let's draw it. So I'm going to take our structure with the radical, and I'm not going to draw all of the phenols out because they're not all relevant, but we can rotate just like you drew the resonance a little while ago. We can draw this like this and get this resonance. Although this specific resonance is not going to help us, which we're going to see in just a second, because it's not in the right place, right? We're not attaching on the side right here. Does that make sense? So we have to draw another resonance structure. So we're going to do that. Okay, now we have a resonance structure that the radicals on the end of that ring. So that is actually what we need to do the reaction. Does that make sense to everybody? Are we following along? We need to have the end of the ring attached right here, so I need to have the radical right there. So all that happens next is that we just couple with another radical. So we just end up with this coupling, which is a termination step, and that gives us that structure, okay? So we are basically just doing a termination step, where it's just a coupling reaction. But first, one of these triphenylmethyl radicals needs to undergo resonance, and we put that radical at the end to get that structure. Is everybody with me? Okay, questions? All right, we're gonna do some more problems. In a second, I'll give you a second to finish writing. So one thing I do want to point out, unlike almost all of our other reactions that we've seen so far, some radical reactions lead us to actually a lot of different products. Radical reactions are really not the go-to reaction for most chemists because you get so much products. The one exception to that is actually polymers. That is one place that radicals are actually really, really helpful. All right, so our next problem on that sheet as well, we're going to be getting an anti-Markovnikov hydroboration. So we see the bromine in that position, but notice that our ring has opened up, okay? So you actually saw something almost like this, but with hydroboration, just regular hydroboration. So we have to have moved some carbons around, which means that we have to have an alkyl shift happening. Something has to cause that ring to get bigger, okay? So we're gonna do that. So first we're gonna break apart our peroxide. This is probably benzoyl peroxide breaking apart. And then that bromine that we get out of that, okay? So we get a secondary radical, but this ring is very strained. We have ring strain. And so our reaction can actually undergo a alkyl shift. And I'm going to label these carbons 1, 2, 3, 4, 5, 6. 1, 2. I'm going to come over here, 4. Okay. So we are going to end up having something like that. And you get your bigger ring. And then you have your next propagation step. Okay, so this is basically just a rearrangement. So radicals are just like carbocations. They can rearrange themselves to give you more stable structures. And we get that product, okay? So the only reason this happens, because normally secondaries never go and form other secondaries, is just because we have a cyclobutane ring, which is not stable, so it's going to rearrange itself to make it more stable. So it is doing exactly what we've seen before, but for a slightly different reason. It's not going from secondary to tertiary. It's just moving from a smaller ring to a bigger ring, which is also helping to stabilize stuff. Okay? Everybody with me on that? All right. One thing that definitely helps with these mechanisms is to number where things are, and we're going to see that when we do polymers, that numbering stuff is going to be very, very, very helpful. All right, so last class we did this problem already, and we did problems just like this, but there's a couple things that I want to bring up with these reactions. So the first one, we know that we generally form our allylic product, and that's our major product. There is a minor product that also happens, and it happens because of rearrangement. So we're going to talk about that in just a moment. And with these, we've seen this before. Actually, I think we did this problem before, or something very much like it. You're going to get two products, and actually the two products, we add the bromine in the benzylic position, but you're just going to get both stereochemistry, okay? So you actually get enantiomers in this product. So we're going to talk about two different things in these questions. The first one is, what is this minor product? So that minor product is actually a consequence of that mechanism. So one step of the mechanism, we end up forming a radical here, and then the bromine comes in. But we could also get a rearrangement of this double bond just because the resulting double bond that we get, we go from a mono-substituted double bond to a tri-substituted double bond, right? So normally we make a radical here, and then the bromine comes in just like we've done before. But a minor product that we get has to do with our double bond undergoing resonance. So for the minor product. And so from here, your bromine can come in and couple. And so our minor product that we get, and I'm saying this because there is a classwork question that is going to ask you about that, okay? So it is a minor product that we get, but it is still a product. This next question says, what happens if we add excess NBS? Like, instead of adding one equivalent or one equivalent, which is oftentimes what we use, let's say we add 2 equivalents or 3 equivalents or 4 equivalents of it. What is going to be the major difference that's going to happen? What's going to happen? We initially get these, but what's going to happen next? Still have a benzylic hydrogen.
You have more than one group?
Yes. Okay, so if you add excess NBS, remember that you have an extra hydrogen here, so you can easily remove that hydrogen, make a radical again here, which is pretty stable, and then add another bromine. So it can happen again. Does that make sense? So if you have extra NBS and you have multiple benzylic positions or multiple allylic positions, you're going to get more of that bromine being added. So watch out for the excess, either X and then S, or written as excess, or it might say 2 moles or 3 mole equivalent or something like that. Okay? All right, our last couple of things that we'll talk about are some mechanisms. So we talked about the benzoyl peroxide as being an initiator and can cause radical reactions to happen. We talked about our BHT as an inhibitor. It can stop radical reactions from happening. And there are, other than medication reasons, there's a couple of places that we see these preservatives, these antioxidants being used. And our two problems that we're going to have are actually related to that. So a couple of things can happen. When you buy vitamins, for instance, like the more expensive, good quality vitamins oftentimes come in brown bottles. If you're like me and get the gummy vitamins, they usually come in like clear plastic bottles because you probably eat them very fast, faster than you're supposed to. Also, they're in the gummy form, so some of this stuff that I'm talking about isn't not necessarily going to happen to them. But vitamins are susceptible to radical reactions because vitamins themselves, a lot of them serve the purpose as actually reacting with radicals. That's a lot of times what we take, not all of our vitamins, but many of our vitamins actually, like vitamin C, in our bodies actually stop radical reactions, which we want to have happen, right? The other thing is there are certain chemicals that are susceptible to radical reactions in certain places, like diethyl ether is very susceptible to radical reactions, and I'm going to draw the mechanism for you for what's happening in the presence of oxygen. This is actually something that you have to be very, very careful of if you buy diethyl ether, that you can only store it for a period of time before you need to discard them because of these radical reactions, unless you have an antioxidant in there to help slow this down, because the product of this reaction is explosive, highly explosive. There are many people who've lost their lives just because they picked up a bottle and actually knocked it a little bit and it just exploded. The whole lab is gone. They're gone. It's a mess, okay? I think the last time I heard about this was probably maybe 10 years ago. There was a graduate student who that happened to, and the whole thing was just awful, right? Because they didn't get proper training on how to handle these things. The other place this is a problem is double bonds because of resonance, so allylic positions, just like the basophilic positions, are prone because of resonance to having radical reactions happen. The problem is oxygen is a radical. Oxygen itself can act as a radical. So just by having air, once I open a bottle, oxygen gets in there. If, and we'll see this in one of our examples, if we look at this for diethyl ether, the first step of this mechanism really is that you have a hydrogen here and that oxygen radical, given enough time, usually this takes like about a year to happen, like to any big extent. It happens before a year. But you abstract your hydrogen from the position next to the oxygen. And again, the reason for this is because of resonance stabilization. So I'm going to draw your product here. So due to resonance, you end up with something like that. So you get some resonance stabilization. But the next thing that happens is another radical can come by. So I'm going to just redraw this right here. Another oxygen molecule can come by. And we get this. So how do we add that hydrogen here? Where do you think that's coming from? What is the only thing in this mixture that has hydrogens? Is it the oxygen gas? So it has to be from here. So something on, some hydrogen coming from here, and I'm just gonna do an R group. Something from here with the hydrogen, we can pull that hydrogen off, and we get this thing. So after some time with oxygen, this happens. If we, and as long as you buy these ethers from reputable companies, they're usually going to come in either very, very dark bottles, like the amber bottles there, or metal cans where light can't get in, or they'll tell you to store it in bulk. And you can store it, store it in cold temperatures. So when I have my diethyl ether, I store them actually in the bottles in the refrigerator to help slow this process down, because heat accelerates radical reactions. I usually buy my ethers with an antioxidant in there, and there are certain metals that can act as antioxidants. So you'll see in the bottom of my ether bottles like a little tiny piece of metal that acts as an antioxidant to help prevent this problem, okay? This also happens with fats. So because we have allylic positions, these allylic positions are also susceptible to this. So the same mechanism happens. I already have one drawn here. I'm going to just draw another one. And the reason that this is important, how many of you have ever had, I'm going to draw this a little bit different, had like nuts that have been sitting for like, you just had them in your pantry for a little while, and they don't taste like awful, but something tastes a little off about them. This is because of that, okay? How many of you have ever like had cooking oil, and after a while the bottle might have a little bit sticky feel, or it tastes okay, but it's just something a little off about it? That's what we call rancidity. It means it's starting to go bad. What's happening is you get a radical reaction, and I'm going to just draw a shortcut right here. Because of the stabilization beside the allylic position, we get oxygen reacting with the double bonds. And then this molecule breaks down into other things that give you these off flavors. So you start getting these aldehydes, and you get all sorts of other compounds. But it basically starts this process, and it does not taste very good. So I mentioned olive oils or cooking oil, and I mentioned fats because you see this, you might have noticed this happening more with those things because they have more double bonds in them. So plant fats, which are more liquidy, have a lot of double bonds. If you take organic too, we'll talk about why that is and how that is. But they have a lot of double bonds, so they're more susceptible. So if you leave your olive oil in the fridge for a little too long, this tends to happen. Or not in the fridge, but in your pantry. So if you go to Publix or Winn-Dixie or wherever you go shopping, and you look in the olive oil section, you'll notice that the top shelf, which is the more expensive olive oils that are like $15, $20, $30, $40 or whatever, they're mostly in cans to prevent light from going in them. They're in dark bottles to prevent light from going in them. And if you're a connoisseur of cooking, they'll often tell you keep your olive oil in the refrigerator. That's all to prevent this from happening, okay? But if it just sits out for a while, if you go to, let's say, Costco, and you buy huge quantities of these things, just be wary that eventually this is going to happen. It doesn't happen as much to animal fats as fast, just because animal fats don't have as many double bonds, but it will happen eventually. And I've been unfortunately the recipient of tasting butter that's gone rancid, and if there's nothing else that like hurts your life ever. That is like, it's the worst and awful tasting thing on the planet, and you'll never forget it. And this has happened to me like 15 years ago, and I will never forget that taste. Nothing tastes like rancid animal fat. It is awful. So, one day I'll tell you why that I ended up eating rancid animal fat. But all right, so which one of these must be the product, and then we're going to do our classwork. Which one of these must be the product of this auto-oxidation happening? First of all, where's the allylic position? Here, 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 where?
Should be like here, and then you go to the topmost carbon, and then you to the left one.
Not really. So our allylic position is always next to the double bond. So that's where our group is going to be added. So our hyperoxide needs to be added in that position, so B must be our correct answer. Okay? All right, so I'm going to give you a little bit of time to do your classwork with your peers. You may need to refresh your page because I'm going to open it up a little bit longer at some point. But work quickly and work with your peers to answer these. Some of these questions I actually already did for you.
Because the double bond and the hydrogen are gonna form a bond. And then wherever that radical goes is where the chlorine's gonna go. So it's gonna go either there or there. Oh, or the radicals are gonna be the secondary. Because it's more stable in the secondary. Yeah, it would go here. And then it would go there.
I don't think it's gonna be the third one because it just.
I'm gonna try it.